Okay. Thanks everyone for listening in on the talk. So today I'm going to talk about scalable and efficient decoding algorithms that use information from flag qubits. And the ideas that I'll be presenting today apply to topological codes, but they can also be applied to other families of codes, as you'll see, subsystem codes as well. And this is based on work in two papers with the authors that you see here. And well, so originally, this work was motivated while I was at IBM from the fact that, we considered quantum computing architectures that were based on fixed frequency transmon qubits. And in this type of architecture, if you want to interact, or if you want to have interactions between neighboring qubits, they need to have different frequencies. But during the fabrication process of the chips, there's some random fluctuations in the frequency assignments, and so on occasion you can have two qubits that are neighboring each other that have the same frequencies, and in that situation you wouldn't be able to do gates between those two qubits, and so that's pretty detrimental. And so if the probability of these events is quite high, then you'd have to fabricate many chips until you get one that has no frequency collisions. So we wanted to have an error correction architecture that minimized the probability of frequency collisions. And from an error correction point of view, one way to do that is to have qubits interacting by nearest neighbor interactions with low degree. And the reason is that when you have a low degree connectivity between the qubits, you don't have to assign as many frequencies on the whole chip, and so the total probability of frequency collision dramatically is reduced. So I'll be talking about three. I'll start by introducing three error correcting codes that are suitable for these types of architectures, and so these will be what we call the heavy hexagon and heavy square codes. And I'll also talk about how you can implement color codes on a graph of low degree. And then I'll start talking about how to use flag-based information to efficiently decode these codes. And again, these methods apply to arbitrary topological codes. So I'll start by introducing the heavy hexagon code. So we call it a heavy hexagon because data qubits and ancillas of the code are not only present on the vertices of hexagons, but also on the edges. So that's where the name heavy comes from. And so this heavy hexagon code is a hybrid between a surface code and a Bacon-Shor code. And just to make it a little bit easier to see which gauge operators are being measured, if you look at the figure on the right, this is an equivalent representation of the heavy hexagon code. The actual code would be implemented by the figure that you see on the left. But just to make it easier to show how to measure the gauge operators, I'll be focusing on the figure on the right. And before going on to more details, I just want to point out that the scheduling that we used here is not optimal in number of time steps, but it is optimal in number of error locations. So it's chosen to minimize the number of locations where errors can happen. And importantly, with the heavy hexagon code, the interaction has at most degree 3. So the connectivity of between qubits is at most degree 3. And so the average frequency assignments, or sorry, the average degree of the connectivity is less than 3. And so this code dramatically reduces frequency collisions compared to, say, the standard surface code, as I'll show you later. So to see that this code is a hybrid between a Bacon-Shor and a surface code, if you look at these red type plaquettes here, so one could measure, weight 4 X-type gauge operator at each of the plaquettes, and then the weight 2 at the boundary. And the product of these would form a stabilizer that you would have for the Bacon-Shor code. And similarly, for the blue plaquettes, because I'm measuring a Bacon-Shor, or I'm doing a Bacon-Shor type measurement, I can decompose the weight 4 operators that I have to measure for the surface code as a product of weight 2 operators. And so the measurement outcome of these weight 2 operators is random, but their product is either plus or minus 1 if you have an error that anti-commutes or commutes with the stabilizer. And so these are these wait4 blue operators are the stabilizers of the surface code, and by measuring products of wait2 operators, we can get their eigenvalues. Now, an important thing to notice is that in this architecture, the two white qubits that you see here when measuring these wait4 X-type operators, these are flag qubits. And the ancilla qubits to measure the parity is represented by the black ancillas, and then the data qubits are the yellow vertices that you see in this grid. And there's another code that we can define on a heavy lattice that also has a average lower degree connectivity compared to the surface code, and this is what we call the heavy square code. So it's essentially a surface code, but defined on a heavy square lattice. And again, for both the X and Z type operators, these could be measured by using flag qubits as an intermediary step, and then the black ancillas would measure the parity of the stabilizers. And again, the data qubits would be represented by the yellow vertices. Now, an important thing to note here is that for the heavy square code, information from the flag qubits is crucial if you want to maintain the fault tolerance properties of this code. Because as it turns out, you can see, for instance, if you look at a blue plaquette, a single Z error, say on this white ancilla, can propagate to 2 data qubits. And what's important here is that this wait2 Z error is parallel to a logical Z operator of the code. So in the standard surface code, one can choose a scheduling where wait2 errors arising from a single fault are always going to be perpendicular to the logical operator of the surface code. But in this case, that's not possible with the scheduling. And so using the information from flag qubits to decode this code is going to be crucial if we want to, maintain the full fault tolerance of the heavy square code. So before moving on, I'd like to really convince you why it's important to look at these codes when you take hardware considerations into account. So if you look here at the average number of frequency collisions for the rotated surface code, the standard rotated surface code, which would be represented by these black curves for different values of frequency fluctuations. And if you compare that with what you get for the heavy square code and the heavy hexagon code, you can see that in some regimes you get orders of magnitude smaller amount of frequency collisions. So that's really where you get an advantage in the fabrication process, and also to mitigate crosstalk errors that arrive in these fixed frequency transpond architectures. Okay. So lastly, while talking about codes, I'd like to mention that you can also implement the color code on a degree 3 graph. So that the standard way that you construct the triangular color code families is to have a tiling of hexagons where the white vertices here correspond to data qubits, and you'd have one ancilla qubit to measure the parity of the stabilizer measurement, or to measure the stabilizers. So what you can do in this case is you can have a smaller tiling of hexagons where you add flag qubits, and so the yellow vertices here are the flag qubits, and the colored vertices are used to measure the stabilizers. And for the color code, even if you don't care about a particular architecture, it's well known that for circuit level noise, just having a single ancilla qubit wouldn't be enough to decode to the full effective distance of the color code. And the reason is that a single fault, could lead to a wait2 error that is parallel to a logical operator of the color code. So, so for the color code, it's really important, if you want to have the full effective distance in the presence of circuit level noise, to have flag qubits to measure the stabilizers. So, given this, what we need now is an efficient and scalable way to decode with flag qubits. And I'd like to mention that, previous work on flag qubits have looked at this problem. But in general, you have to have some kind of lookup table that grows exponentially with the size of the code. So it's not a very scalable approach, even if it does work for arbitrary distance codes. So in order to keep the discussion simple, I'm going to focus on the heavy square code, but the methods that I'm going to show you here also, again, they apply to topological codes in general. And we also, implemented these for the heavy hexagon and the color codes. But for the color code decoding, it's a little bit too involved to explain in a 15-minute talk. And so just to keep things simple, I'm going to focus on the heavy square code. So the heavy square code is, again, a surface code. So, the standard way that you would decode this code is you'd have a graph for both X and Z type stabilizers. And I've shown an example of this on the left for a distance 5 surface code, in this case, the heavy square code. And, one would you can either do min-weight perfect matching, or as in the talk by Nicolas that you heard earlier, you can do union find. And so the edges here correspond to data qubits, and the black vertices correspond to the ancillas. But now I'm going to add these extra vertices that are represented in green, and these correspond to the flag qubit measurement outcomes. And so for the example of the heavy square code, there are 2 possible flag outcomes, because there are 2 flag qubits for each weight 4 stabilizer. And if a right qubit flags, then you can show that the possible data qubit errors are either a qubit on the edge E4 or a weight 2 error on the edge E3 and E4. And there's also a possibility, of course, that there's no data qubit error, for instance, if you have a measurement error. And similarly, for a left flag, you have an error on E1 or an error on E1 and E2. So these weight 2 errors, the way that I represent them is to add a cross edge to the matching graph. And this edge doesn't correspond to physical qubits, but if the edge is chosen, then you would project to a weight 2 data qubit. In this case, E3, E4, or equivalently E1, E2. And these edges are going to have infinite weight unless a flag qubit occurs. So the idea behind decoding with this flag information is to say, well, consider a disk that has all possible edges that could be afflicted by an error in the presence of a flag. In this case, these disks have the shape of a boomerang, so I call them boomerang edges because there's 2 possibilities, either, like I said before, a single data qubit error or this weight 2 error, data qubit error, which I represent by the cross edge. And the idea is going to be to dynamically renormalize weights that are inside these disks, or in this case, the boomerangs, and outside of the boomerangs. And the reason I say dynamically is because at each time we measure the syndromes of these codes, there could be different flag qubit outcomes. And so we have to update our information and take that into account. So as an example here, the figure at the bottom right of the screen, imagine I have, say, 2 Z data qubit errors, and it would correspond to these 2 highlighted vertices. And suppose I have a flag error or an error that results in a flag, and it's a right flag in this case. And so I'd have edge weights within this boomerang that I'll show you in the next slide how to compute, and then the edges outside of the boomerang, which would be renormalized based on the flag outcome. So now the key question is, how do we renormalize these edge weights? So given that I don't have too much time left, I'm basically going to give a very high level explanation for how this works. And if you want to see more details, you can of course read the paper. But the basic idea is the following. So suppose that I have M flags, and by a flag here, I mean either a left or right flag for each stabilizer. Just to point out, in this particular example, if a stabilizer has both flag qubits that are measured non-trivially, that's a situation that you don't really care about, because you can show that the data qubit errors that arise from that scenario are always going to be benign. So you really have to consider only the case where you have either a left or a right flag. So that's what this M here corresponds. It's basically the number of stabilizers that have either a left or right flag. Now, the basic idea is to say, look, if there are M of these flags, any data qubit errors or data qubits that are afflicted by an error that don't belong to these boomerang edges must occur with a probability that's order p to the m plus L, where L is greater or equal to 1. Why? Because each flag outcome occurs with probability p, right? And so if there's an error that arises somewhere else on the heavy square code that doesn't arise from a flag outcome, a non-trivial flag outcome, then that has to be this higher order event. So the probability again is p to the m plus L, where L is greater or equal to 1, depending on the particular configuration. And so the basic idea is that we're going to say, well, for for edges within these boomerangs, well, we know that there was a flag here, and we know that we can compute the probability to leading order in P of these edges being highlighted. And then for all edges outside of the boomerangs, we're going to take the original probability that's computed in the case where there's no flags, and then multiply them by P to the M. And you can show that by doing this trick, if you have a particular set of highlighted vertices and you choose the wrong path, so you choose a path that results in a logical failure, that path will always have higher weight than if you were to go through a path that goes through these boomerangs, renormalizes edges, and actually corrects the data qubit error. And so you can guarantee that any error rising from d-1/2 faults or fewer will be corrected by using this trick. And I'd just like to conclude the talk by just showing some numerics, the performance of these codes, and compare that to the standard surface code. So the surface code in this case would have the highest average connectivity, and the heavy hexagon would have the lowest average connectivity. So the threshold for the surface code is around 0.7%. And if you compare that to these other codes, you get around 0.45 for the heavy hexagon, but this is only for one type of error, because the heavy hexagon is it's a hybrid between a Bacon Shore and a surface code. So the other type of error, say the Z error in this case, would not have a threshold. But for the heavy square code and the triangular color code, they have thresholds of 0.3% and 0.2%. So they're quite competitive in terms of threshold with the surface code, but they have much fewer frequency collisions, and so would be more suitable for an architecture based on fixed frequency transmon qubits. So that's the conclusion of my talk. Thank you.
Thank you, Christopher, for another interesting talk. So again, as normal, can we please have all the questions for Christopher in the Slack channel? So we'll start with a question from Jikanti May. Can this flag decoding scheme be effectively adapted for codes with stabilizer weights greater than 4?
Yes, so the color codes have stabilizer weights that are 6, and if you read the color code paper, that's exactly what we did. We adapted these flag techniques to the color code, which has stabilizers weight 6. And in general, these methods can be adapted to stabilizers of arbitrary weight. Now, the challenge when you go to higher and higher weight is to find a configuration of flag qubits that basically would always flag whenever there's these problematic errors that arise from a smaller number of faults. But in principle, if you have that configuration, then these methods can definitely be adapted.
So Peter Morgan asks, can you compare and contrast topological error correcting codes with other classes of error correcting codes?
What was the first part of the question, sorry?
Can you compare and contrast topological error correcting codes with other classes of error correcting codes?
Yeah, so that's a pretty general question. Other competitive codes for that are promising for the architectures that are currently being developed are subsystem codes, and in principle, one of the reasons is that you have these lower weight gauge operators that have to be measured, and these can be done using nearest neighbor interactions. In some cases you need long range connectivity. So in general, people like topological codes because you can measure the stabilizers of these codes with nearest neighbor interactions, and they have often pretty competitive thresholds. If you look at subsystem codes, in some parameter regimes you have also good performance, and then of course there's these families of LDPC codes which encode a lot more logical qubits than you would with topological codes. But there's still a lot of work that needs to be done with LDPC codes to see if you can get competitive thresholds and decoding schemes that work, and if you can implement these on an architecture that's suitable for the constraints that we see with the physics on the chips that we're currently building.
So a question from Jonathan Conrad is, how does the dependency of the logical error probability on the code distance change with the measurement error rate of the flag qubits?
Well, so in general, for simplicity, if you take all of the error rates to be, say, order p, then the logical error rate scales as p to the d plus 1 over 2. And again, these techniques are chosen such that you get the full effective distance of the code. So if you have different parameters for measurement errors or gate errors or things like that, you'll still be able to correct any data qubit error that arises from at most d minus 1 over 2 faults. So the scaling is roughly p to the d plus 1 over 2, even if measurement errors and gate errors and data qubit errors have different rates.
Okay, so thank you again, Christopher, for an interesting talk. There are a couple more questions at Slack if you'd like to head over there. It's my pleasure to close the day and say thank you to all the speakers today for a set of really very interesting talks and really great things. The poster session is still going on, so if people haven't been to look at the posters yet in the poster channel, please do. There are a great number of interesting posters from lots of very clever and bright people. Looking forward now to tomorrow, we will start back tomorrow morning at 11:45, and I look forward to seeing you all then. Thank you for all the interesting talks today.